Maxime Flamand from the 5G Automotive Association. We are gathering more people right now, so I'm waiting a few more seconds before starting. Okay, again, my name is Maxime Flamand. I'm very pleased here to welcome you to this 5G AA online session to introduce a new release study on Dynamic V2X use cases. We have invited 4 speakers during this 1-hour meeting to give you these findings and insights from this study, which basically try to look at use cases in a different range of dynamic situations from different intersections and vulnerable road user interactions, soft maneuvers also, and even high-speed rear-ending. So these are different kind of use case that are requiring some additional very low latency reactions from the automotive systems, and for which both direct and network-based communication have been assessed in this. So we will go through the 4 speakers, namely from Qualcomm, from Vodafone, from CATT, and also from Anritsu, to enlighten us on these different use cases that were assessed. Perhaps we can spend a little bit more time on the QR code to make sure that everyone has time to scan this. This is the technical report that is now online. You're very welcome to download it and then browse through it during the presentation. Please also post your questions through the Q&A panel. We will gather the questions until the end, and then I will moderate these questions. Don't hesitate to ask questions during the presentation so that we don't forget for the rest. But make sure that we will also we will make sure that we try to browse all the questions at the end of the 4 presentations, so that we give the time for the speakers to give their inputs. With this said, I would like to welcome the first speaker, and Ahmed, welcome. You have the floor.
Thank you, Maxime. Let me take control. Hello, everyone. My name is Ahmed Farhan Hanif, and I'm from Qualcomm, and I'm based in Paris. So I will be going over the use cases related to intersection safety. So I will quickly first describe the details and the assumptions around this intersection safety use case, and then the subsequent results that we got from this use case. So for this intersection safety use case, we have a VRU. It can be a bicycle or a moped approaching an intersection, and an ego vehicle also approaching from the bottom. And the ego vehicle has a green light, and the VRU here has a red light, and the VRU is transmitting V2X messages on PC5. Then we have several assumptions related to the speed. The VRU is approaching the intersection at 25 kilometers per hour. its assumed deceleration is 3.4 meters per second, length of the VRU, and it can have, like, the position of the GNSS error can be plus minus 2 meters. For the ego vehicle, we are assuming 60 kilometers per hour, and then the maximum assumed deceleration of 4 meters per second. There is also the reaction time of the driver. In this case, we assume it to be 1 second. So if a message is received, after which it might take the driver at least 1 second to react to that message to decelerate. So here we assume a non-line of sight situation. So this can be a building, and the ego vehicle does not see the VRU, but the messages that are transmitted by the VRU are broadcast messages related to the position and the speed of the vehicle and the direction of the vehicle, based on which the ego vehicle can make a decision and an assumption that if this VRU continues to approach the intersection at a given speed of 25, and when it is 7.1 meters in this case away from the intersection, it means that with the assumed deceleration of 3.4, it won't be able to stop entering the intersection. So based on these assumptions, the ego vehicle can be alerted that there is a dangerous situation at the intersection. And if I go to the next one, so here we have like a progression at time t1, at time t2, and at time t3, what can happen. So we define a window where several messages can be transmitted. So the ego vehicle, the VRU is transmitting these V2X messages at every 100 milliseconds related to its position and speed. And with a reaction time of 1 second, you can see the ego vehicle has displaced, and ego vehicle has displaced and the VRU has displaced. Then at time T2, we are just approaching the center of the intersection, and the ego vehicle has already started decelerating. So that the red line here is showing that the deceleration from time T1 to T2. And at time T3 is the time we define where the ego vehicle has exited the risk zone. So if these messages, or in this slide, are received, like the first message that was received is the message which was successfully decoded and can be used to alert the driver, then the kinematics show that there is a gap of 7.4 meters from the intersection. So we are able to slow down from 60 to 25, and the ego vehicle, the VRU is exiting the risk zone as shown here. Then we have a second situation where several messages, like every 100 milliseconds. So we have a window of 0.66 seconds. So if we decode on the last message, so the sixth message, so in that situation, the ego vehicle will displace a little bit further, and the VRU will also be displaced further. And then the final picture will look at time T3. You can see the gap from the intersection is 1 meters. So we are entering just when the VRU is leaving. So this is like the most dangerous case, but it's the last time where you could have reacted. But if we were to react, if we were to not receive that last message, then it's like a safety critical scenario. So this is the kinematics. Then I will show you the analysis of the reliability of the messages. So if there is no GNSS error related to the position of the VRU, then the action window in which we can receive those messages is 0.66, which corresponds to 6 V2X messages that can be received. So either we react on the first message or the last message or any of the messages in between. So based on which message we react on, the position of the VRU from the intersection is changing, the ego vehicle's position to the intersection is also changing, and the ego vehicle to VRU distance, like the direct distance, is also changing. And based on these, the distance between the ego vehicle and the VRU, we can from simulation results, we can pick up the PRR, packet reception ratio. So we can have different packet reception ratios for each of the messages. And here at the bottom, I show for all these cases the probability of success. So we can have either a low density vehicular scenario, medium density, or high density. And the worst case is when you have a GNSS error of, let's say, -2. So, and a high traffic scenario. Just to quickly show the, going back to the picture. So here I drew this circle showing GNSS error uncertainty. So the reported position might not be the true position. There could be a ±2 meter error, and that error can also impact the results and the window size. So that's what we are showing here. We can have a GNSS error of -2, GNSS error of +2. +2 means you are 2 meters away from the intersection. -2 means you are 2 meters closer to the intersection. And the 2 meters closer actually shrinks our window and makes the use case a little bit more challenging. So you only have 3 messages to work with, but when you are farther away from the intersection, the +2 meter GNSS error expands the window. So it's 9 messages can be used. So when we have 9 messages to work with, the reliability goes up. So that's why I was focusing specifically on the worst case, which is here. So high vehicular traffic plus a GNSS error of -2. And with this, we can get 4-9 reliability. If we have medium, then we have 5 nines. And if we have any of the others, like if there is no GNSS error, you can see, though even in the worst case, in terms of traffic, we can be at 7 nines. So this is a scenario between V2X and ego vehicle. Then we have the same scenario, but vehicle to vehicle. So a violator vehicle, another one approaching at 60, has the same assumptions related to deceleration of 4 meters per second. It's transmitting its messages to the ego vehicle, and the ego vehicle needs to make a determination if the violator vehicle is approaching at a given speed, and when it is 34 meters away from the intersection, it means that it won't be able to stop in time, and that's the danger scenario, and which triggers the ego vehicle to decelerate. And if I show the pictures for this, it's the same. So 34.7 meters is our point where the use case gets triggered. There is 1.1 seconds of reaction time. And after the reaction time, the violator vehicle has displaced here, and the ego vehicle is displacing equally. Then you have 2.68, where the ego vehicle has already started decelerating, and the violator vehicle is approaching the risk zone, the center of the intersection. And at 2.58, you can see it is the whole, we assume like a 5 meter long vehicle, and it is exiting the risk zone. And we will still have a few meters before we are approaching the risk zone. And this is the assumption if we are acting on the first message and we are able to successfully decode the first message. If we are not able to decode on the first message, then we are in this scenario. The window size in this case is 0.74. So we can have 7 V2X messages. So here we are talking about the 7th V2X message. So a time of 0.74 seconds has elapsed. The violator vehicle has displaced accordingly, and the ego vehicle accordingly. And then T2, we are entering the center of the risk zone. Then 3.58, the violator is exiting. But in this case, the margin of approaching of the violator exiting and the ego entering is only 1 meters. It's still a safe scenario, but it's like at the edge. So if we were not able to, if we had not received that 7th message, we would not have decelerated sufficiently enough for it to be safe. So if there is a 8th message and we react on that, it won't work. So all these numbers, they were chosen based on assumptions to demonstrate PC5 capability to be used as a safety intersection safety scenario. So here you can see the same picture, but for a violator vehicle to ego vehicle, you can have a GNSS uncertainty of -2, 0, or 2 meters. And then with -2, you can have 6 V2X message opportunities. If there is no GNSS error, you have 7. And if it's plus 2 meters, you have 8 message opportunities. And in terms of reliability here, you can see the worst case is with -2 and high traffic density. It's still 7 nines. And yeah, the rest of the analysis is similar. The only things that have changed is instead of the VRU, we have a violator vehicle, and the vehicle length is 5 meters, and the decelerations are different. So the kinematics change, and that changes the window, and that changes the number of message opportunities that are available for these use cases. Then there is another use case which we did not go into detail, but I would just like to introduce this use case. So we have a soft intersection approach use case using SPAT. So SPAT is a signal, phase, and timing. So the traffic light can transmit these SPAT messages, and these SPAT messages can be received by approaching vehicles, and it tells when traffic light is going to turn from green to yellow to red, and when if you are approaching on ACC, adaptive cruise control, the vehicle can based on it adapt its speed in such a way that it approaches the intersection in a soft way. That's why we call it soft intersection approach, instead of relying on sensors or visually looking at the intersection and applying abrupt braking for these scenarios. And so we did not go into the analysis of reliability for the SPAT messages for this, but this is introduced here, and this will be covered in future 5G AA works. Then to conclude quickly, we presented here the day 1 messages related to PC5. So we had the ego vehicle to VRU and violator to ego vehicle. And based on the results presented, you can see that PC5 is capable of handling this, the assumed speeds, and including the reaction times. So the reliability in the worst case is 4 nines, and for violator vehicle it was 7 nines. So yeah, that. For details, please have a look at the report, and that's all from my side. Thank you.
So Tony, you're muted.
Thank you, Maxime. Somebody had to do it. So it might as well have been me. Yeah, I'm going to present a use case around vulnerable road user presence awareness in the case at which the vulnerable road user is a pedestrian crossing at the mid-block. I've included a picture here to show it's a relatively simple use case, but you can imagine in this case we have the vulnerable road user pedestrian equipped with a personal device such as a smartphone connected to the mobile network, with an approaching vehicle also connected to the mobile network, which is receiving messages which are describing the pedestrian's position and direction. You can imagine, of course, a much more complicated scenario here where there are vehicles or other things that are blocking the driver's vision of the pedestrian. And we, of course, have to point out that in the mid-block, there's no support from either a defined crossing point or any roadside equipment such as cameras or LiDAR to support the situation. So it's purely the driver's vision, which could be blocked by either parked vehicles or bad weather, and the information that we are giving to the driver is purely to give them an early warning, an over-the-horizon warning, which may be beyond the capability of onboard sensors in this scenario. So moving on to the next slide. It's a much simpler model than the previous presentation, because we can make some assumptions about the reliability of messages that are sent via the mobile network, and we can just simply use the latency of the mobile network as the main variable, and of course the objective of the model here is to understand primarily whether the mobile network, a standard optimized mobile network, is able to convey these messages in a reasonable time, such that the driver gets the information. And now, the other assumption in this model is that once the driver receives information, the goal here is not to enact any kind of emergency stop or collision avoidance. The object is for the driver to slow down at a comfortable rate, at a maximum kind of comfortable deceleration rate, such that by the time they reach the expected crossing point, the vulnerable road user / pedestrian will have already managed to cross through the lane, and therefore will not be in any danger of a collision from the driver. And at the same time, the car is not expected to stop and to stop traffic. It should continue to move through. So it's a kind of an advanced warning and a managed interaction with the VRU. So that's really the overview of what we're trying to find in this model, and we approach it differently in effectively trying to understand the point at which that warning or alert message needs to be delivered to the driver, such that they can deliver the experience that I've just described. As I just mentioned, our main question is, can the mobile network appropriately support the use case? And for the model, we've got a number of parameters. I've already mentioned the mobile network transmission latency. We don't have any problem with the reliability of delivery here. The other variable parameters are the driver's reaction time. We have drivers that react immediately when they receive an alert, but we also have to assume there are drivers that will react that may be otherwise distracted and will take a longer time to react. And we also introduce smartphone position inaccuracy as well, and that's inaccuracy on the part of the vulnerable road user. So other parameters that are input into the model are, of course, the vehicle approach speed, which we assume is the local speed limit for urban or suburban scenarios. Here in the UK, where I'm based, that's about 30 miles per hour, which translates to about 50 kilometers an hour. We assume a maximum comfortable deceleration rate of 0.3 G, which is about 3 meters per second squared. And we have a standard pedestrian crossing speed of 5 meters per second, 5 kilometers per hour, and a lane width of about 4 meters. That's a single lane, because of course we are only clearly interested in the VRU clearing the lane that our vehicle is within. And the output is really, as I said earlier on, the minimum distance between the vehicle and the pedestrian for which that alert must be delivered. So as a further illustration of this very, very simple model, on the left we have the pedestrian crossing, the vehicle approaching, and the various geometry associated with that, as you can see. But it's worth looking into the position error here, which we've illustrated as a circle around the real true position of the VRU, which is the black spot in the middle of the diagram on the right. The red spot is the actual reported position, and what we are showing here is the worst case error, where the position of the vulnerable road user is in the top left quadrant. What that means is that not only is the actual crossing point closer to the approaching vehicle, but the VRU is further away from the start of crossing the road at that point that it's reported, and therefore the vulnerable road user will actually take a lot longer. So in this case, we have to introduce a compensation for this worst case position error into the calculation, which we will now illustrate the main results for. So without introducing the position error, we very simply calculate that the pedestrian takes just under 3 seconds to walk across this lane. And a fast reacting driver would need to receive that message about 45.8 or 46 meters away from the pedestrian's crossing point, for which they will then need to slowly decelerate. And it's worth stating that we assumed an extremely conservative end-to-end transmission and service latency of 300 milliseconds in this model, which is very large for a 4G, 5G mobile network. We've seen more realistic end-to-end latencies of around 20 to 30 milliseconds in our demonstrations. And in this case, the actual use case, so the 300 milliseconds is a small component of that overall time taken to enact this use case. A slower reacting driver, who would be reacting in about 2.5 milliseconds, would need an additional distance to receive that message, react to the message, and then apply the comfortable deceleration rate. And that separation rate increases to 66.6 meters within this model. But now, if we introduce our position error of 2 meters, the worst case that we described, we can see the distances at which this alert should be delivered to the driver, and it's worth stating that the vehicle, the system onboard system of the vehicle, can decide based upon constantly received information when to deliver this message. That the message should be delivered for a fast reacting driver at now just over 61 meters, and a slow reacting driver pushes all the way out to about 82 meters to give that alert. Now, if you will then move on to the discussion of the implications of this now. The conclusion, as I've already stated, is that the latency as imposed by the mobile network, the 4G, 5G mobile network, is very low, and at the very conservative value that we applied does not have a huge impact on the scenario, and enables the scenario with good time at a very comfortable deceleration rate. However, as presented, the worst case conditions cause the time taken for the vehicle to reach the crossing point to be much higher. We assume that the driver, who cannot see the vulnerable road user for whatever reason, we assume, reacts to the alert and starts to decelerate comfortably once they react to the alert. But given the GNSS error, and now on the assumption that there is error and that the vulnerable road user has actually crossed the road quickly, and that the crossing point is a reasonable distance, is not the reported distance but a further distance, by the time the driver approaches the crossing, that vulnerable road user will have crossed a while ago, and the driver is now in danger of looking at this information and considering that the service now has been delivered far too conservatively. So even though we've identified that the scenario is well within the capability of the mobile networks, we are now considering the fact that the error due to the smartphone, that the smartphone position inaccuracy, may render this service very difficult to deliver. So the conclusion here now is that we need to start to look at the capability of personal devices to support these use cases in low VRU velocities, and we encourage improved position accuracy for such devices if we want to then start to introduce services based upon these technologies. That's my conclusion. I'll hand over to Li Xiao now. Thank you.
Thank you, Tony. Hi. Hello, everyone. I'm Li Zhao from CTT. I'm very happy to share the presentation with all of you. In fact, this scenario, high-speed car-to-car rail, is selected from the 2024 version of ThinkCap scenarios. This use case want to address the rear-end collision scenarios on highways or straight road, and for this picture, there are three vehicles. The rightmost is the stationary vehicle, and in the middle is the leading vehicle, and the leftmost is the eagle vehicle, VOT. In these scenarios, there are two distances. Distance A is between eagle vehicle and the leading vehicle, and distance B is between leading vehicle and the remote vehicle. And
Li Xiao, we don't see. Hello, Li. We don't see your next slide. So if Alessandra could help to play the next slide, thank you.
Hello.
Thank you, Li Xiao. The floor is yours. Thanks.
Hello. Thank you. Thank you for the notification. And in these scenarios, we want to utilize the assumptions from the ThinkCap 2024. There are two distance A and distance B, and there are two speeds, 80 kilometers per hour and 120 kilometers per hour are considered. And the distance A is set as 50 meters and 100 meters with different speeds. However, in the ThinkCap CCRH scenarios, the deceleration is not implicitly specified. So we utilize the assumption from the FCW Ford collision warning and the AEB testing with the non-emergency deceleration as 4 meters per second squared, and in FCW emergency braking scenarios, 7 meters second squared are utilized, and these assumptions we aligned with the analysis in Qualcomm and Waterfall. And we utilize the similar methodology of the risk zone to define the region which the eagle vehicle may collide with the leading vehicle and the remote vehicle. To reflect the real conditions, we further analyze the assumptions. For example, the relative vehicle speeds, the conservative and aggressive driver reaction times, and the non-emergency and emergency deceleration. So we have analyzed 4 scenarios. The first one, scenario 1, is with the most loose requirements for the assumptions. For example, the non-emergency deceleration of 4 meters squared per second squared is summed, and the end-to-end transmission distance can be calculated, and the reaction time is 2.4 seconds thus, the reaction distance can be calculated as T1 equals to 53.3 meters. The braking distance then can be calculated as 61.6 meters. So the total distance from V2X message reception to a complete stop is 117.1 meters. After accounting for the distance covered by the leading vehicle during the cutout maneuver, the required initial longitude distance between the eagle vehicle and the leading vehicle is about 68.1 meters. Thus, we can calculate the distance for the leading vehicle risk zone and the remote vehicle risk zone. It can be observed that in these risk zones, the distance can be covered by the communication range of the PC5 direct communication. Then the second scenario 2, we utilize the aggressive rapid reaction time. Thus, the total stopping distance can be decreased after the message reception, and the risk zone can be further decreased. And for the scenario 3, we utilize the assumption of the emergency deceleration and with the same speed of the eagle vehicle VUT and the leading vehicle VT. And it can be observed that the total distance after the message reception is 71.9 meters, and it is further decreased. This results in the the last scenario 4, is the most stringent requirements for the analysis. This scenario is fixed deceleration with emergency deceleration, but the speed of eagle vehicle is higher than the leading vehicle, and this results in the minimum relative separation distance of 8.9 meters, and similar as the analysis in the Qualcomm, though the distance is is at the edge, but the safety can be guaranteed, and it can be observed that the distance in the risk zones can be protected by the communication range of the PC5 direct communication. So it can be the conclusion can be achieved. The CCH scenarios is based on the high speed is inspired by the ThinkCAP 2024 standards, and the analysis demonstrates the effectiveness of the PC5 direct communication during the sudden cutout maneuvers. The analysis tested various highway speeds and following distances where a leading vehicle unexpectedly changed lanes, revealing a remote vehicle ahead. The finding confirms that under both emergency and non-emergency braking assumptions, the required deceleration distance consistently falls well within the PC5 direct communication range, ensuring adequate response time and effectiveness mitigating the collision risk within the identified safety zone. Thank you. That's my presentation. We welcome your valuable suggestions and comments. Thank you. I will pass the ball to Mr. Johnson Borry from Andrews. Thank you.
Hello there. Yes, thank you, Li Xiao. So this is Jonathan Borrell from Anritsu. Going to talk to you now a little bit about the field measurements and available data sets for V2X. So some of the critical KPIs that have been discussed in the modeling scenarios in the last 3 presentations, we want to take a look at the the real world measured parameters that we could see. So talking about the data sets first for MEC deployment. So when we look at the MEC deployment, we were using a data set that was based upon the 5GAA MEC for Auto architecture. So we were having vehicles connected to a MEC system. So through a local MNO. In the trials that we did here was both T-Mobile and Vodafone, and then connected to a user location on the MEC here, which was coupled.
Jonathan, we also have a little problem with your control, so please, Alessandro, please, can you make sure that you're showing the right slide? Thank you.
Okay, do you see the
floor is yours. Yeah, we see the data set now.
Okay.
Okay, thank you very much, Jonathan. Sorry for this glitch. Thanks.
So the first data set, as I said, is looking at data sets for MEC deployment, so using the V2N network mode. And in this scenario, we used the 5GAA MEC for Auto architecture. And we had a vehicle connected to a 4G, 5G network. In these trials was both a T-Mobile and Vodafone network, and then having a application server located on the local MEC. So the local MEC here is with the application server and with a timestamp service coming from a local MTP server. What we could see when we drove this route was the number of parameters. We were able to record the latency, both the downlink latency and the uplink latency separately. And then we were able to also confirm all of the network settings. So from the mobile device, what the receive power was, which network it was connected to, which cell, what signal to noise ratio. So we could correlate all of the latency events with any radio performance or network events. In addition, we could also record the GNSS availability during the different trials. What we could see from here, so this trial was done, we're using the MNO network from Deutsche Telekom and the RAN and the MEC coming from Deutsche Telekom, so entirely this system here. We saw a downlink latency where we had a mean value of 6.2 milliseconds, the standard deviation, so plus or minus 1 sigma of 2.5 milliseconds. Correspondingly on the uplink, we had 36 milliseconds uplink latency. Uplink latency is normally longer because of the way that the cellular network scheduling works. But to look in more detail, we were actually then able to compare the latency over a certain reliability probability. So we could see, for example, on this drive test here, 99.9% of all packets received within 14 milliseconds. So we could say that 14 milliseconds could deliver this level of reliability. And this reflects back to the previous presentation from Vodafone mentioning what kind of latency figures they were assuming in their modeling. So, as you said, this was collected during the 5GA demonstrations on the T-Mobile network. Downlink latency at an average of 6.2, but the 99.9 percentile was at 14 milliseconds. What we could see was the number of satellites was generally available, but there was some scenarios in downtown where the GNSS availability was low for this scenario. We also then looked at a data set for a central cloud deployment. So in this central cloud deployment, we were comparing different locations, this time across the US. So we were connecting from New Jersey, connecting to back-end servers, which are in Dallas, Detroit, and New York. So having different distances between 150 kilometers and 2,500 kilometers. But we can start to see now what is the latency with these types of different distances. Again, we saw that the average latency was around 30 milliseconds, and the closest location at just 150 kilometers was at 17 milliseconds. But even when we looked at 5 nines here, so 99.999% of all packets, was still falling within the 100 milliseconds latency. And this is valid even for the longest distance of 2,500 kilometers. So these figures showed us that we were able to maintain this type of latency. This testing was done on the Verizon 5G network, where the MEC service is provided by the AWS wavelength service. What we could also see that is for the Dallas and Detroit locations, they had almost the same average latency, despite being quite different in their distance. And what this highlights to us is actually not only the distance away from the data center, but also the transport network capabilities. So often there are switches and routers in the network which can cause this additional latency and additional long tail on the latency. So we could see that the differences were apparent on the shorter distances, but after around 900 kilometers, the latency difference was not so much comparing on different distances, but still within the 100 milliseconds for the 5 nines. We then repeated some data sets now looking at the PC5 direct mode communication. And we could see here that the PC5 direct mode from one modem to another, the latency actually falls within a much tighter constraint. So here we were falling within 13 milliseconds minimum and 28 milliseconds maximum. And this is for 10 packets per second with different types of payload size. So we found the PC5 to be very robust to the different payload sides, and also very robust to the latency bounds, that no data was falling outside of the first bound. And even as we increased to 100 packets per second, so 10 milliseconds in between, we were still able to maintain a very robust performance. So what this showed us was that the PC5 mode was extremely robust in its latency bounds with no long tail effects. Moving on then, the second area that we considered for data sets was the GNSS data set. So in the previous discussion talked about the GNSS error. So in this campaign, we set about using a commercial smartphone. So we initially used the Oppo One Plus with the Qualcomm Snapdragon mobile platform chipset. And then we later moved to using a Google Pixel 9 device. In these scenarios, we tried in the dense urban environments, we tried in the suburban environments, and we tried in some open skies environments. So we could see the effect of buildings and reflections. Also, we considered the user activity. So was the user holding the device in their hand in front of them? Was the user having the device in a jacket pocket, or was the user having it in their back pocket? And full sets of data were selected for all of these locations, all of these types were analyzed. Just as some example, so here's an example in London of a mixed urban scenario using device held in the hand in front of us. What we found was the accuracy reported error was down to 3.8 meters. Initially started at much higher as you walk from an indoor building to an outdoor building, but the reported accuracy from the device here was 3.8 milliseconds. We also then could move to a mixed urban where we now put the same device but into the back pocket rather than being handheld. And what we saw was a much bigger difference, that the reported error could be up to 11 or 13 or 15 meters. And this we think is due to the fact that the device in the back pocket has got much less access to GPS or GNSS satellites due to blockage from the body itself. We also then moved to another open skies scenario here in Sacramento, but we changed device. So we changed the Pixel 9 in the handheld. So this was in a very good situation where it was open skies, it was held in the hand. And here we found the accuracy to be reported down to 1 meter. So in this scenario, we could achieve quite well the requirements that were shown in the previous presentations. So as conclusion, we could see the latency KPIs, and that the latency KPIs themselves were within the bounds that we talk about for the modeling in the previous sections, that the V2N network mode was achieving 6 to 8 milliseconds average latency and 14 milliseconds for the 99.9%. We saw the Met Cloud architecture that even at distances up to 2,500 kilometers, we were getting downlink latency average of 36 milliseconds with 100 milliseconds for the 5 nines. We saw that the PC5 mode, all the latencies were well contained within the 13 to 28 milliseconds with no long tail effects. And finally, for the GNSS availability, the GNSS reported accuracy, we could see difference between the two different types of device that we used. And then we could also see a difference between how the user was holding the device, whether it was handheld, whether it was in a jacket pocket, or whether it was in the back pocket of the user. So with that conclusion, I'll hand back over for the Q&A.
Thank you very much, Jonathan, Tony, Ahmed, Lee. This was very good overview of the report, which of course looks a little bit technical, but at the same time digs into some usual use cases that we see in V2X and that we talk about, and then it's always good to put a little bit of number around the use case that we test and that we demonstrate. And so I really appreciate this report. We have a few questions. We'll start with the first one here, and this concerns the three first use case shared. There seem to be best case scenarios of reliability in terms of reliability, and in terms of real life scenario where you may have additional traffic and wait 2 seconds. So you may have traffic from different sides of the intersection. How have we compared this with some real life scenarios where you get these additional vehicles that are sending, but perhaps not necessarily relevant to the ego vehicle? I think that this goes to Ahmed.
Yeah, I mean, in terms of the assumptions, we had the 3 traffic density scenarios. We have the low, medium, and high density traffic, but these are still based on simulation assumptions. They are not based on realistic traffic data. So maybe as a next step, if we want to have like field trials, or before field trials, we can have like data that can be used, and that. But it would be indicative, at least in this case. This is indicative of the type of reliability that we can get. But to answer the question, it's still not based on realistic data or field data. Yeah.
Jonathan, would you have had a chance to simulate anything with PC5 on with additional let's say interferer or additional?
Yeah. So the data I presented was bench testing of real modems, so real PC5 data link, and showed it to be very robust within the parameters we use. So we fully loaded the link. Of course, when you overload the link, there can be some additional latencies involved, but certainly the data we showed was real measured data and showed the PC5 to be robust to heavy loading.
So another question that we got, but I got that through the chat. I don't know how, because I thought that the chat was disabled. But for PC5 test measurements, which radio technology was used? Was it LTE V2X or NR 5G V2X direct? I assume it was LTE V2X that was in the test.
The data I presented was the LTE PC5.
Yeah. Okay. Good. And so that's good clarification. Now there is another question to Farhan on issues related to, so how do we translate this into situations where you have more automated driving maneuvers rather than driver reaction? How does that modify the way we build the system?
So if we assume autonomous scenarios, then maybe we can modify the reaction time. So right now it's based on a human driver's reaction time. So later it can be translated maybe like zero reaction time. We can get rid of those, and we can get more closer or more higher reliability because the window can expand, and we can receive much more messages, and so it can operate in a more worse scenario. Or it could be also like weather conditions. We have not taken those into account. That can change how the car decelerates or accelerates. Snowy conditions. So, but those are like can be part of a future study. But at least here we provided a model to demonstrate that PC5 is a robust technology for these safety for the intersection use cases.
Thanks, Farhan. I got another question here popping up. Did you analyze the measurement error or latency vector statistics, uncorrelated versus random error latency? And that goes to Jonathan. Do you want me to repeat?
Yeah, just repeat, please.
Did you analyze the measurements error or latency vector statistics?
So certainly the latency statistics we analysed for the distribution curve to see what type of distribution was involved. Was it just some random effects? And certainly the latency side, you could see some more systematic effects, as I said earlier, which is perhaps more due to network switching type of thing. From the GNSS reported error, we've not been able to analyse the distribution curves of the results, but that can be done in later study. As I think, as Tony said, we need to look further into this whole topic of the GNSS reported error.
Thank you. I got a thumbs up from Ernst, who asked the question. I have another question here for Li Xiao, related to the test case from China and CAP. To what extent the sensors on board the vehicles are also used to initiate or to warn the driver? Is this test only based on the V2X information, or is it also using the sensors?
Thank you, Dr. Maxim. Currently, the analysis in the technical report is only based on the V2X communication. And in fact, we have done a survey of the sensors, and we have summarized the state of the development of sensors handling in the industry. And because currently V2X communication can be considered as one type of the sensor, and the data fusion is utilized for the ego vehicles to provide the functionality such as automotive driving. So we can collaborate with other experts to conduct the research on the advanced use cases such as automotive driving, and such kinds of advanced use cases to promote the research of the cars. Thank you. Thank you very much.
Thank you. So some more research may be needed. How do we combine optimally the V2X information on one side and the sensor-based information on the other side? Okay, I see that the time is running, and so I have another question here for Tony. So you mentioned this challenge with regards to the positioning of the vulnerable road users. What is 5G exactly doing about this issue? Is there any activities?
Yeah, it just happens that we have another work item called Vulnerable Road User Awareness and Protection, and we're looking really at the barriers and the path to market for vulnerable road user V2X based services, and we've identified. Smartphones could be an amazing way of communicating vulnerable road user positions and intentions to enhance safety, but we've identified the GNSS inaccuracy as a potential barrier to market in certain use cases. And of course, the alternative of that would be the deployment of roadside infrastructure to support that. But we've identified it, we're looking at it, and we'd like to have some insight into perhaps the manufacturers' roadmaps to improving GNSS on personal devices. So we'll be incorporating aspects of that into that work item and publishing that sometime towards the end of this year.
Okay, thank you, Tony. So we are coming to the end of this meeting. I see the top of the hour. Perhaps we can show you this last slide with regards to the QR code, so you can download this report. There is much more details into it, so I really encourage going in depth. Don't hesitate also to relay some questions to us. There is always an eagerness from our expert to answer any tricky questions. So don't hesitate to pose questions to the secretariat, to me, or to even to the individual experts, and we will just make sure that we answer as soon as possible. So with this, I really thank the speakers. Well done, and thank you for this great report. I'm sure there will be more, and stay tuned. Thanks.